let's talk about the intuition. We've got a switched source. I'll make it as simple as possible with the U of T. And we've got a inductor and a capacitor and a resistor, and they are all in series. So your intuition is that there's pump, and it's pumping through some sort of restriction. And then it goes through this long coiled pipe that has a lot of inertia to flow. And we've got a diaphragm here. There we go. Okay, so we've got we've got this pump over here. And when let's evaluate what's happening intuitively with current when we suddenly step this thing on. So this is a step response. So when we turn it on, all of a sudden, before we had no current flowing at all, and now we've got current flowing. But it's going through this really, really long pipe that's got a lot of inertia. Now this capacitor here, this diaphragm, starts off discharged, so there's no voltage pressure across it at all. So it's not resisting anything. It looks like a short. But the thing that's resisting current flow is the resistor, and it's the inertia of this pipe. And in fact, because of the inertia of that pipe, if we were to graph the current flow, and I think a lot of intuition is done by looking at current. The resistance would limit the current flow to something small, but immediately positive. Right after that pump switched on, it would be present. The inertia of the pipe, though, forces that initial current flow to be zero, exactly zero, no matter what that resistance is. Now then, after a while, this inertia starts to build up in the pipe, and it allows the current to flow. Now, as long as this capacitor is mostly discharged, it's going to increase its current flow. And after a really long time, eventually, if not for that capacitor, the current would be only limited by that resistance. But it's never going to get close to that, because as that current flows, it's going to deform that resistor. And so that resistor is going to develop a bigger and bigger voltage pressure. It's the area underneath this curve. That's the amount of charge that's flowed. That's the amount of charge that's pushing that resistor in. It's the area underneath here it's this area here that corresponds to an amount of total water measured in gallons, which is how much this is distending. And after a while, you'll see that it starts to develop such large voltage pressures that it's going to stop this increasing. And in fact, eventually, if this resistance is really big, it'll slowly stop, and eventually the current will stop. And when the current is stopped, the voltage pressure across here will be equal to the voltage pressure across here. If this was 1 volt, there'll be 1 psi of voltage pressure across here, and we'll stop. And it was so slowly took to get to that point because of this big resistance. So this is if it's overdamped intuitively. Now the damping coefficient of a circuit is measured by an equation called alpha. The more the alpha, the more damped it is, the bigger the resistance is, and the slower it takes to end. The amount that it wants to oscillate is omega naught. So here we have an alpha that's bigger than our omega naught. But what happens if we bring our resistance something smaller? We make it look like this. We still have to start off at 0 because of the inertia of the inductor. But now what we're going to do is get a much bigger, much faster initial current flow, because as this inductor starts to allow current to go, it's not going to be really limited by that resistance much. That means that this capacitor is going to charge up a lot faster. And so therefore it's going to build up a counteracting voltage much faster. And we'll see that current drop down much faster. Now, if the resistance is small enough, it'll actually overshoot. We'll actually get the capacitor going in this direction. And the reason for that is that once that capacitor starts getting starts getting current starting to flow in this direction, as it's starting to, this capacitor is going to reach its maximum point right here. As it starts to collapse in, the current becomes less strong, and it will eventually move in the opposite direction. There'll be inertia in the pipes that will allow the current to move a little bit in the opposite direction, even opposing this voltage source. That'll bring it down here, and it'll oscillate around here. This is called underdamped. It's what happens when the tendency, when your damping coefficient is much less than the tendency to make it oscillate. And this omega naught describes not its oscillation frequency, but what its oscillation frequency would be if R was equal to 0. And from that, you might guess that there is some intermediate point at which R is not quite so small that it makes it oscillate, but not so big that it takes a long time to even out. And it goes high, but not terribly high. And it goes down just fast enough that it doesn't quite overshoot. And that's called critically damped. And at that point, alpha equals omega naught. And that's the fastest we can have our circuit settle down to 0 without oscillating. So how is that? That's a lot of stuff. How is that, John, for an intuitive approach?
I think that was really helpful. Thank you, sir.
Cool. Okay, then let's get on to our lesson.